Imagine performing a measurement so gentle that reality barely notices you're there. And yet, the answer you get back is something the universe should never allow. A number that sits far outside all known physical limits, mocking everything you were taught about how the world works. This isn't a thought experiment. It's a real result, pulled directly from laboratories around the world. When physicists first saw these outcomes, they stared in disbelief. They recalculated again and again, hoping for an error that never appeared. Because the equations were correct, the experiments were repeatable. And the results were deeply, deeply unsettling. Something inside quantum mechanics was speaking in riddles. And it was calling these riddles weak values. To understand why weak values are so disturbing, you have to first understand how measurement normally works. In the classical world of Isaac Newton, measurement is passive. You look at a spinning top, you measure its speed, and the top keeps spinning, essentially unchanged. You observe, but you don't interfere. Quantum physics destroys that comfort completely. In the quantum realm, the act of observation is an act of intervention. It's like forcing a shy person to answer a direct question in a crowded room. It's like trying to hear a whisper in the middle of a rock concert. So physicists came up with a clever trick. They repeat the measurement thousands, sometimes millions of times, and then average the results. This helps the faint signal emerge from the noise. But weak values add another twist, one that seems to bend time itself. It's called post-selection. Here's how it works. First, you prepare a group of particles in a specific initial state. Then, you perform your series of gentle, weak measurements. Finally, and this is the crucial part, to only keep the data from those particles that end up in a very specific final state. You throw everything else away. The system is defined not just by its past, but by its future. Preparation and outcome now work together, squeezing information out of the present moment between them. And when this time sandwich measurement finally reveals its value, the number is often impossible. This is where all our intuition completely collapses. Weak values can fly past the maximum values an observable is ever allowed to have. Others claim they are nothing more than contextual illusions, entirely dependent on how you set up the experiment. Yet, the uncomfortable truth remains. Weak values consistently predict experimental outcomes with extraordinary precision. Illusions are rarely this reliable. One of the most shocking demonstrations of this strangeness is known as the Quantum Cheshire Cat. In these incredible experiments, a particle appears to travel down one path of a device, while one of its properties, like its spin, travels down a completely different path. The particle and its property behave as if they are no longer bound together. It's like the grin of the Cheshire Cat from Alice in Wonderland, floating in the air without the cat itself. This separation is real, measurable, and has been reproduced in labs. Weak measurements reveal a world where particles are not solid, indivisible objects, but are more like loose collections of properties that can, under the right circumstances, go their separate ways. Weak values also challenge our fundamental understanding of time. Because post-selection uses future outcomes to define present measurements, the system behaves as if the future is influencing the past. Now, to be clear, no information is actually traveling backward in time. Causality, the rule that cause must precede effect, is not violated, but the probabilities of what ULL measure in the present are reshaped in a way that feels uncomfortably retrocausal. The arrow of time still points forward, but our intuition about what causes what begins to crumble. Once again, quantum mechanics obeys its own equations while quietly betraying our common sense. Weak values turn fragility into a superpower. By listening carefully to these quantum whispers, scientists can extract information that a brute force, strong measurement would have destroyed. Perhaps quantum mechanics isn't describing objects at all. Perhaps it's describing relationships between how a system is prepared, how it's measured, and what its final outcome is. Instead, it's a responsive system that answers questions differently depending on how they are asked. A strong measurement demands a certain answer and gets a limited one. A weak measurement asks politely and receives something richer but far, far stranger. Measurement is no longer a window into reality. It's a negotiation. Some interpretations of quantum mechanics see weak values as revealing the average behavior of quantum systems, not where a particle asterisk is asterisk, but how it statistically exists across all its possibilities. A theory where time symmetry is fundamental, where past and future coexist on equal footing, and where certainty isn't a basic feature of nature, but just an approximation we impose on it. What truly unsettles physicists is not the mathematics of weak values, but their philosophical implications. They suggest that by trying less hard to control reality, we can actually learn more about it. That our demand for certainty might be the enemy of true understanding. Weak values reward humility. They reveal that the universe does not respond well to force, but it responds generously to patience. History shows us that every major revolution in physics began with numbers that made no sense.